Okay, so the next bit that we're going to have a look at is electron configurations. So what we need to do is look in a little bit more detail about the electron configurations in comparison with what you did at GCSE. So on the piece of paper, could you write down the electron configuration of sodium, please? Okay, so you can see the periodic table up on the wall there, or in your folder or whatever, but just in rough, we'll have the electron configuration of sodium. Right, what have we got down for the electron configuration of sodium? Cool. Have we all got 2.8.1? Yeah. Okay, so we've got from the atomic number, tells you it's 11 protons, which is the same as the electrons in the atom, 2 in the first shell, 8 in the second shell, and then we've only got one more we need to worry about anyway, so 2.8.1. Okay, so we have got our GCSE style electron configuration. So we've got 281, and then we've got what would be, well, a dot diagram rather than dot and cross diagram there in particular of a sodium atom. So what we need to be able to do is move from that to that. So with your neighbour or neighbours, can you see if you can spot any similarities and any differences?
Oh, okay then. And then it has 2. Yeah, 2 is 3 to 8, and then the 3 makes the 1. So the 3 makes the 1. Yeah, because on the big number there's 1, and then the power to the power of, I don't know, 2. And then the other 2, the 2s, both 2s, and to 8. You make 8. And the 3 makes 1. But what is 3?
Right, so what have we spotted? Middle row. I won't pick anyone in particular. So is there anything that kind of links in between the two? Did you come up with anything between you? Ali, what did you go? Excellent. So what might those numbers be telling you?
That's how many, the ones that like to the power, that's how many electrons there are, and
that's okay. No, that's good. Okay, so those numbers that are like powers, it would make sense then that they're going to give you the number of electrons. So we've got, in our GCSE, we had 2 in the first shell, and then we've got a 2 here, and then 8, the 2 and the 6 add up to 8, and then 1, we've got the 1 over here. Excellent. Anything else? Right, go on, Lily.
The big number, the electron shell that it's on. So 1 is the first, 2 is the second, and 3 is the third.
Yeah, that makes sense as well, wouldn't it? So yeah, so we know that that first number 2 was the first shell, and we've got a big number 1, which could be 1 for first. The 8 were in the second shell, and these ones added up to 8, and they began with 2. And then same with the third shell. That's absolutely right. Anyone know anything about the letters? Yeah? Almost, not the shell, but subshells. So yeah, that's the right kind of idea. So the kind of logic of looking at it in the first place, well, particularly having a look at the second shell, so 2s2 and the 2p6. So that's suggesting that our 8 electrons aren't kind of all in the same environment, and that they're split into a section that's got 2 and a section that's got 6. And each of those sections is what we call a subshell. And then subshells are further divided into things called orbitals. And so the first slide said shells, subshells and orbitals. So that's how we get it. So a shell is like a GCSE shell. Okay, so that's just what you know already. There are up to 2 electrons in the first shell, 8 in the second shell. And then because you only ever looked up to calcium, we could say then there were only 8 electrons in the third shell. But as soon as you hit the transition elements, so from scandium through to zinc, that they actually have their outer electrons in the third shell as well. And so that means actually we can have 18, but you didn't need to know that information at the time. So it wasn't a lie, it was just only applicable up to calcium. Some people go, oh, but you lied to us. So no, we just simplified it so you could get your head around it. Okay, it's never a lie. Right, so we have our energy levels or shells, split up into subshells and then split up into orbitals. So what I'm going to do is carry on talking you through this stuff, and then we probably won't have time to write anything down, and we'll do that next time, because I think it's a good thing to kind of go through, come away going, oh, that's kind of a bit weird and tricky, and then go through it again right from the beginning of the PowerPoint, noting stuff down, and then sometimes it kind of settles a little bit then. So you've got kind of 2 shots at trying to understand it, and then lots of practice anyway. So there are 3 kinds of orbitals. So we can have s orbitals, which links with where on our sodium electron configuration we had 1s2 and we had 2s2 and we had 3s as well, didn't we? And they're spherical, okay? And there's only ever 1 s orbital in a particular shell. We can have p orbitals, and we say they are dumbbell shaped, and they are always orientated so that the crossover bit is at the origin. So if you imagine 3 axes, so you've got x-axis, a y-axis and a z-axis, and people at home, you won't be, oh, actually, no, maybe I can get you to see this bit, hang on. That is if I can get that to stop for a minute. Right, let me go to the ladybug for a second. Let me see if I can, right, this is where you need 3 cases. Right, so if you have your x-axis, your y-axis, and your z-axis, okay, so just have 3 axes perpendicular to each other like that. Okay, does that kind of make sense? And then you have one of your p orbitals coming vertically up and then down, one of your p orbitals going horizontally around that one, and then one of your p orbitals coming out towards you guys and then back towards me. Okay, so they're all at 90 degrees to each other, which is where we can have our pencils like that. Then we have d orbitals. You'll be pleased to know you never need to draw these. Okay, so d orbitals are like double dumbbells, and the first 3 go between the lobes of the axis. So these ones are dxy, dxz, and dxz. And then we have one that goes along 2 of the axes and one that's got a donut in. So it's like a p orbital with a donut. So all of these orbitals give you regions of probability, and they're the places or the areas where electrons are most likely to be found, because electrons are moving around all the time. So it's just kind of a probability distribution of where they are most likely to be found. There are also things called f orbitals, which get even more annoyingly complicated, and we don't need to draw those either, which is very useful. Now, the number of these correlates with your periodic table, and you can find chunks of the periodic table that will correspond with the number of orbitals you've got. So if you have a look at group 1 and 2, we often call that area of the periodic table S block, and all the outermost electrons in group 1 and 2 will have their electrons in an s orbital, because all orbitals can contain 2 electrons. If you then have a look at groups 3 to 8, there are 6 groups there, and that corresponds to your elements having their outer electrons in p orbitals, because if you've got 3 p orbitals, you can contain 6 p electrons, and there are 6 groups there, so that we sometimes call that p block. We've then got 2 sections left, so we've got the chunk in the middle, the transition elements from scandium through to zinc and below. And we've got the lanthanides and actinides, which are not on your home periodic tables, but the one we've got up on the board, those are the lanthanides and the actinides in those 2 rows at the bottom. So So which area is going to be called D block and which area is going to be called F block? So transition elements, are they D or F? Yeah, D. So we've got 10 groups of transition elements. So that corresponds to the 10 electrons that the 5 d orbitals can hold. And then your lanthanides and actinides, if you've counted how many groups there are 14. And that corresponds to, sorry, that's down here, to the 7 orbitals that can contain 4 electrons. That are the F orbitals there. We'll look at how we can much more easily work out what's going on in each of them, but we can look at those later. So we say that a subshell is a group of orbitals of the same type within the same shell. So your 3 p orbitals in the same shell make the p subshell. An s subshell, there is only one s orbital in each shell anyway, so there's only just an s subshell is just one s orbital. It doesn't do anything exciting. Orbitals within a subshell, we call them degenerate, and they have the same amount of energy, so they're equivalent to each other. They're just orientated differently around those axes. And so we can say that the p subshell has 3 degenerate p orbitals, those 3 that we saw drawn out. Any d subshell has 5 degenerate d orbitals, and an f subshell has 7 degenerate f orbitals. Okay, and we've just seen all those diagrams. And then a shell, right down at the bottom there, is a complete group of orbitals having the same principal quantum number. And that's the principal quantum number is the big number at the beginning, it's the shell number. So when we had to look at sodium, we had the 2s2 and the 2p6. So that was the shell, the second shell, because it had this, all the orbitals there had the same principal quantum number at the beginning. Okay, we can fill that in later, we'll ignore that. Right, there are rules for filling shells, and then we'll have a look at how this actually comes about. So, when you're filling shells, we always fill the lowest available energy level first. And you did that at GCSE. You filled the first shell first, then the second shell, and then the third shell. You didn't just scatter your electrons randomly amongst any shells that you fancied. So that's just the same. Now, electrons behave as spinning particles, and you can only have 2 types of spin, and we denote this with arrows. So they can have, an electron will be a half-headed arrow, and it can either have kind of up spin, if you like, or down spin, but the arrowheads need to be in the corresponding places like we've got on the diagram there. Then we have what we call the Pauli exclusion principle. So if 2 electrons occupy 1 orbital, they have to have opposite spin. You can't have 2 electrons spinning in the same way, they have to be opposite. So you can have the electrons in 1 orbital. Orbitals are often drawn as boxes. So you can't have them both with down spin, you can't have them both with up spin, but you can have them with opposite spin. So the first situation is allowed, the other 2 situations aren't allowed. In Hund's rules, when 2 or more electrons occupy a set of degenerate orbitals, so if you've got lots of orbitals where they could go, first of all, they occupy them singly, and then secondly, they'll occupy them with parallel spin before spin pairing in any one orbital. And this is a bit, we sometimes think about this as the strangers on a bus kind of rule. So you've got a bus, it's got 3 seats. Each of the seats can occupy 2 people. 2 strangers get on the bus. Where do they sit? Not next to each other, absolutely. So first person comes on, takes the first window seat. The next person will come on and will also go and take a window seat because they're cooperative and they're not annoying. Okay, so that's the same as having single occupancy and with parallel spin. Okay, so we wouldn't put the second electron like the other way around. And then the third person comes on and sits by the window as well on the same orientation. Next person comes along. They couldn't possibly face the first person because they might actually have to have a conversation. So they look the other way. So they're spinning in the other direction. Okay, and then you can keep going and fill up. All right, so you always occupy each of the orbitals singly first with parallel spin before you have what we call spin pairing. So that's like seat sharing on a bus. Okay. And then we've got this diagram here, which later I've got a little printout one, and this shows you the order in which orbitals are filled. So when we have our shells, this is the first shell because it's got principal quantum number 1. And in the first shell, we only have an s orbital. In the second shell, we have s and p. So the s subshell, if you like, there is only one s orbital, so you can have up to 2 electrons in this. And then in the p subshell, there were those 3 degenerate p orbitals, so we can have up to 8 electrons in this. So we're agreeing with GCC at the moment, 2 electrons in the first shell and 8 electrons in the second shell. Once we fill 2p, we then fill 3s. So that can take 2 electrons. Our p can take 6 electrons. And that's where we start like moving on from GCSE, not moving away. So that would correspond with your 8 GCSE electrons from that shell. Because now, after P, our energy levels start overlapping. And I've got an overlapping diagram to show you later as well. And next, we fill 4s, which takes us up to potassium and calcium in terms of where our electrons can go. And so that was the extent of what you had to know up to. So we didn't worry about how many electrons went in that shell because we only got up to 2 of them. However, in the third shell, there is also the D subshell with its 5 degenerate D orbitals, which can contain 10 electrons. We can map this to the periodic table. So with our very first 2 electrons, that's hydrogen and helium at the top. After hydrogen and helium, we get lithium and beryllium. So their next 2 electrons go here. And then we get boron through to neon. Those 6 elements, we're playing around with electrons into P. After that, we get to, where am I now? Sodium and magnesium. So that's 3s. Then we go aluminium through to argon. That's 3p, play around with those 6 electrons. And then we're filling 4s because then we're potassium and calcium at the end of GCC now. But next after calcium on the periodic table, there's scandium through to zinc, so 10 elements there. And those elements have their outer electrons in the 3D shell. So you always have to remember, if you're using the periodic table to help you with that electrical configurations, that as soon as you go from calcium and 4s, you have to drop down to 3D for our scandium. And so that means if you count up all of these, you've got 18 electrons there, and your third shell can contain 18 electrons. And then we carry on. But there are various ways of remembering how to fill things. Interpreting the periodic table is probably the easiest, but writing out this and just knowing how your arrows go is one way of doing it. Some people like doing it that way. Okay. So, and that was how the energy level diagrams overlap. We'll worry about that a bit more next time when we go back to the beginning and recap this. So, lots of diagrams. Just to show you then, before we finish, how we get from 281 to the electron configuration I showed you at the bottom. So, applying our rules, we're going to put our 11 electrons in from the bottom, and we're going to spin pair. Then we can fill up the next shell. So we put them in there, spin pairing. The 2p, we fill individually, but we need to fill it completely, so we go back and fill them the other way around. And then our 3s, we've used 10 electrons so far, so our outermost electron goes in the 3s subshell. We don't need any 3ps because we're not going to use those. We'll use those next time. So that's how we get from one to the other. Most of tomorrow probably will be the practical. We'll see if we actually get time to revisit this, but we will literally go back to the beginning. You'll have a piece of paper in front of you. We can go through and get the notes down that we need for this. And then my next slide after this one is one for you to have a go at. Okay, and then just practice, and then it'll soon come together.